Yeah, so I'm going to present the status of the MSOS pipeline. So I will start by present quickly what I'm going to speak about. So what are our goal and expectation? I'm going to describe a bit the photometry pipeline that is mainly developed by Sebastian Ho with the help of Jay. I'm going to present the event pipeline, which is more the modeling of the light curve and the lens flux analysis, and I will quickly speak about our plans for this year. So first of all, the MSOS team is the Microlensing Science Operations System team at IPAC. The MSOS lead is Rachel Atkinson. And then we have sub-team, especially Sebastiano Calcinovati and Iju Zhang are mainly focused on the MSOS photometry, or how to extract the photometry from the data of Roman. Me and Kito, we are more focused towards the development of MSOS events. Wangi, Jennifer, and Emmanuel Joliet, they are in charge of more tasks like put the glue everywhere needed. And Alexander and Kai, they are working on the detection efficiency, which is one of the projects we have to return to the community to make the planet demographics analysis. So quickly speaking, the exoplanet microlensing survey will try to will observe the Galactic Bulge about 6 seasons or 70 days, and the goal is to detect about 30,000 microlensing events, and it will be 1,400 planets according to a paper from Matthew in 2019. So here I describe kind of the old design, which was 7 fields, 6 seasons, 60 days, 15-minute cadence. And overall, that represents about 40,000 epoch per field, and 1,000 epochs for the other filter. And on this design, it was expected to have about 200 million stars in our catalog. So this will be updated based on the CSS survey. I'm not sure about the acronym that recently came, but that will not change dramatically. So we have several requirements at MSOS that we need to achieve. The first one is we need to measure the planet mass function between 30 mass and 1 Earth mass at better than 15% per decade. We also have to measure the frequency of small mass planets between 0.1 and 0.3 Earth mass at better than 25%. We also have to measure 40% of the host mass and distance actually at better than 20%. And we should be able to measure the frequency of free-floating planets in the Water Galactic Bulge, and also the frequency of Earth-Sun system in the data. So these bullet points are really the main points that we use to design our pipelines. This is really what we need to achieve at MSOS. We also have some kind of resource and timelines constraint. Notably, the photometric pipeline has to process 5 terabytes per day in real time during the seasons. And of course, when you design such a big pipeline, we are focused on the overall precision. We don't really care about each event individually. Actually, the analysis of difficult case, such as triple lens or double source, etc., will be the charge of the bit. So we start our pipeline actually by the photometry, and it starts with what we call level 2 image. So this level 2 image have been processed at the SOC, so at the Space Telescope, and they take care of the rounding of the sampling of the ramp, as well as artifact elimination, right of pattern maybe, etc. So we assume that all of this calibration is done before we start our pipelines. So this is a quick view on how that works. So Roman observed the field, and the image are downloaded to our SOC, which is at Space Telescope. Here, take care of the basic calibration towards the L2 data products. This image are sent then to IPAC, we call that the style of center SSC. We run our photometry and event pipeline, and then we send back to SOC what we call level 3 and level 4 data products. So, for example, the stack image that Jay was speaking previously, it's called level 3 data, while level 4 is more star catalogs or event classification and things like this. Then it's the responsibility of SOC to make this product accessible to the public. It will be done via MAST. And then the product can be used by the community and notably the migrants in it. So as I say, the MSOS photometry, it has to process 5 terabytes per day of every image in less than 48 hours. So that means as soon as we receive an image, we have 48 hours to process it and to send it back to SOC. We have a requirement on the level of precision the pipeline should achieve, which is a scenarios of 100 for HAB star at brighter than 21.4. We're going to have several times the pipeline running, so we have a real-time processing, but we will run the entire pipeline for the end of season, so that's with the current design 5 times, and the overall survey at the end we will run this. And the computing is done on the NASA Mission Code platform. It's kind of AWS platform. So for the photometry, the notable product will be star catalogs, especially contain magnitude and astrometric solution. Of course, for example, the astrometric solution will not be meaningful or even filled after 1 or 2 seasons. You really need 3 or 4 to have something for all the data. We're also going to send back the reference frame. I will go back to this. And for each image, there will be PSF photometry for all the stars detected, as well as DIA. And this process of delivering the data will not start before the first 30 days of the survey, because we have some kind of initialization to do during the first 30 days. So for the photometry, long story short, we basically use as a EPSF infrastructure that Jay described much better than I do, so thank you, Jay. So the idea is to take benefits of the high sampling of the field to conduct a novel sampled image called the stack. So that's been decided to use 8 days of data, which is about 750 images, to reach a novel sampling of 8 for each image. And then you can use this reference frame to do catalog search, but also it's the base of a DIA. You can estimate the DSL, etc. So if you want more detail, I invite you to go back to the talk of Jay. And here are some preliminary results for a star. On left, you can see the photometry obtained from full simulation of image with a pre-century PSF. It's a 20.6 star, so we are not at 21.4 yet. The RMS is about 1%, and the astrometric precision is about 1 million seconds. And you can see here the DIA on the same star, it's almost the same precision, slightly better, but for the case of DIA, we fix something. So both of the products will be delivered at each epoch to SOC. So for MSOS event, our requirement is to classify and find the microlensing and model the microlensing events. We have to take care of the lens flux analysis. We need to find the physical property of the lens, like mass, distance, etc. It's going to be run only at the end of each season, and actually all of our requirements for events are only for the end of the survey. It's running on the same cloud as photometry, so it's the NASA Mission platform. So we're going to deliver a viable catalog, so each source will be classified. Is it, I don't know, periodic or something like this. We're also going to deliver a microlensing catalog, and we plan to deliver all the MCMC changes we make during our analysis for the community to play with. The exact format will have to be decided, but we plan to deliver that. And we're going to deliver for each microlensing event an event summary. Okay, I'm going a bit quicker. So the classification is like a decision tree like this. So we have various steps, and each time the reply is no, we go to the next one. And if it's not flat and not chromatic, for example, it will end up as a Microlensing candidate and start to be modeled. Here is another result example of the classifier right now. I don't have much time to discuss about it, but it really kind of works good. The event modeling is like this. We start with a single lens, single source. We try to add parallax if needed. We try to add final source if needed. And if it doesn't work, we just go on binary modeling with RT model. And if we don't know what it is, then it will end up in this unknown. And this will be for fun for the pit. But if we find a decent model, then we run Markov chain, and then we go to the mass estimation. Yeah, so the lens flux is kind of the same structure. We start with 1-star model, and then a 2-star model, and if the result is satisfying, then we go to same to Monte Carlo Markov chains, same logic. And to estimate the physical parameter, we plan to run this part of the pipeline for all the lens because we think that it's informative to have also for single lens. Despite it's not in our requirement, this is quite of cheap. Plan to use pipeline.
Necessarily complicated.
Last year with Sebastian and Marcus. Here is how can look a summary page for each event. So we plan to have a light curve, kind of a view of a stamp around the target, some kind of CMD and mass estimation summary. So if you want to add something, you can speak to us, and we are happy to add things. And I think I'm done, so I will stop there and take questions. Thank you.
Yeah. I may have missed, but are you finding the new event which are not registered on the reference image? So the source is fainter than the.
Do we do source extraction from the different stack? So looking for evidence in the different image detection? No, we don't do that. It's not in our requirement yet.
Why not?
It has been designed like this.
Okay, so if you want to do that, you have to, somebody has to do it separately.
Yeah.
So are you going to keep all the different images?
That's under discussion. But if the community really want to have access, so right now the different image will not provide it to the community, but if, because that had significant volume of data, but if this is something the community really wants, that we should start the process to make some requests that we
want to hear that, yes.
we're gonna have to ask some more resources.
Do you expect many such events?
I don't.
Actually, it doesn't need to be the tech making process, anyone who can. That's things.
So, yeah, we've been discussing whether you get some of the difference images saved with the project. And Will DeMago had a discussion with a small bodies group at the University of Maryland, and they're super excited about this. They consider it a huge opportunity that they had no clue and would never have checked on themselves if you had. So I think it's a way that Roman could add to a wide range of scientific